Welcome back for Concept 2 in our Relation and Function unit. And we are going to be talking about linear versus non-linear functions. So a linear function sounds just like its name. It's a function that forms a straight line. We learned all about this last unit as being y equals mx plus b. So everything we learned in that unit applies here today. So we're going to put that in right here. So a linear function is a function whose graph is a non-vertical line. So what this really means is that they want us to write a linear function using a graph. Well, you are literally going to use your y equals mx plus b, take this generic template like we talked about before, and apply it to this line. So they didn't draw the line in, but that doesn't mean that we can't. Now, there's going to be two steps to this. We need to find our y-intercept and our slope. That's how we take that template and make it unique to this question. So the first part is finding your slope. Now, we did this in a couple different ways before. If we had our picture, we were able to just look at the graph, right? So let's do both to kind of refresh your memory, because I know it's been a long break from that. So if we start at these 2 points here, we go down 1 and to the right 2. So our slope is -1/2. I think we practiced that enough that you probably remember that one. If not, that's okay. Then we also had a formula. That was the change in y over the change of x. So what you need to do is find the ordered pairs of these 2 points. So we have -2, 0, and 0, -1. So we're going to plug into our formula. So -1 minus 0 over 0 minus -2, which becomes +2. Hey, look at same thing. Pretty cool, right? So we have our y equals -1/2 x plus our b. Remember, our b is our beginning. That's on the y-axis, saying where does the line touch the y-axis. So if we look here, we have that nice spot right there at -1. So we just put in -1. There you go. By graph, I think that's probably the easiest way that you're going to be able to write a linear function. Now, we are also going to look at something like example 2, where we have to use a table. So you can take the time and plug in these points on graph paper and get your straight line and do the same thing that we did in example 1. Or you can listen up here and see what we're going to do to solve it a little bit differently. Now, our y-intercept. So we have find m for step 1. And step 2 is y-intercept. So we talked about our y-intercept, and that is when x is equal to 0. So when that happens, you're going to look at your table and see if you have an x equals 0. Hey, that's right there, isn't it? So what is the output, or your y? It's at 2. So our y-intercept in this case is at 0, 2. So we're going to use that for advantage. That's fine. And to find our slope, these are all just ordered pairs. So if I take the ordered pair -2, 2 and 1, 2, I can plug back in to my same formula right here. Like I said, you could graph it and go through all that, but I think it's actually almost easier to do it this way. So I plug in my y's, change in y over the change of x, Remember, minus -2 becomes a +2. 2 minus 2 is 0 over 3. 0 divided by any number, excluding 0, would just be 0. So our equation is y equals 0x plus 2. But we don't really need to write 0x. You can just say y, oops, ran out of space here, y equals 2. And if you look here at the y, do you see how they're all equal to 2? This would just be a horizontal line. So if I erase this here, it would show that. This is just a line at y equals 2, which we've talked about before. Let's move on. Now remember, if at any point you need to pause and rewatch, do so. So let's look at an application of this. So in example 3, you are controlling an unmanned aerial vehicle for surveillance. The table shows the height y in thousands of feet of the UAV X minutes after you start its descent from cruising altitude. Descent means that it's slowly going and getting closer and closer back to where you're at on Earth. So in part A, write a linear function that relates y to x, interpret the slope, and y-intercept. So we are going to do the same thing that we did in example 2 and 1. We need to find the equation of the line. So if we look at this, do we have our our y-intercept right there for us? No, that's when x equals 0. So we have that here of a y-intercept at 65. So we plug that in for our b. Now, we also need to find our slope. So you are going to take 2 ordered pairs. It doesn't matter which ones you pick. I tend to pick one from the beginning and one from the end just for my peace of mind. So that's what we're going to do here. So I'm going to pick the ordered pair I already have boxed there. And the one at the end is fine, or the next one down. It really doesn't matter. Pick the bottom one. And we are going to plug into our slope formula and find out what this rate of change is. So we plug in our y's, so 65 minus 50 over 0 minus 30. So we get 15 over negative 30, which does reduce down by 15. So if you divide by 15 to each, we would get 1 over negative 2, or negative 1/2. So our equation is y equals negative 1/2 x plus 65. So they want us to find the height of your UAV when you stop the descent after 1 hour. So imagine you're controlling this vehicle, little motorized vehicle, for an hour, and you want to know where is it at in the sky at that moment. Well, 1 hour is 60 minutes later. And if you look here at minutes, that represents what variable, your x or your y. That's going to be key to understanding where to plug into your formula. And if you notice here, we're all at x's. So that means that you need to plug in the 60 wherever you see an x. That's all you're doing. So y equals negative 1/2 times 60 plus 65. Remember, 65 is just that initial height of this vehicle before you start your descent. So it's at 65,000 feet. Because remember, everything's in thousands of feet. So if I plug that in, I get negative 30 plus 65. So y equals 35 feet. So instead of being at 65,000 feet, you are now at 35,000 feet. So part A wanted us to interpret the slope and y-intercept. Your y-intercept is your initial height of your object, and your slope is telling you a negative 1/2. So you're going down, because it's negative, you're going down a half each and every time a minute goes by. They want you to be able to understand that concept along the way. Okay, our last topic for the day is nonlinear functions versus linear functions. And remember, the word linear means a straight line. It's the constant rate of change. So your pattern is the same each and every time. A nonlinear function, so in our little space here, nonlinear function, does not have a constant rate of change, so its graph is not a line. So when you hear about functions and all these new words, it can sound kind of daunting and scary. But if you can remember that linear means constant and nonlinear means not constant, it's really easy to tell the difference between them. So what does this mean for us mathematically? So we are given these two tables here to start off. We need to figure out if they're linear or nonlinear without graphing them. So let's look at the patterns. To get from 3 to 6, it's plus 3. 6 to 9 is plus 3. And 9 to 12 is plus 3. Constant rate of change, so far so good. Let's check it out down here. Minus 8, minus 8, minus 8. Hey, were they constant? Did they change at all? No. So they are linear because the rate of change was constant. I wish everything in math could be like that. It's not so scary after all, is it? All right, part B. You guys know me. I like to give you an example of each to refer back to. So hopefully this one will be nonlinear, but we'll have to be able to explain why if that's the case. So we're going to check our x's. So 1 to 3, that's a plus 2. 3 to 5 is a plus 2. And 5 to 7 is a plus 2. All right, not bad. So down here from 2 to 11, that is a plus 9. 11 to 33, oh man, that's a plus 22. And then 33 to 88 is a plus 55. So what should grab your attention right now is this right here. Is that a constant same change each and every time? No, definitely not. So this would be non-linear. So it forms a graph that is not a straight line. And we would say because it is not a constant rate of change. So make sure when you're taking these notes that you are not just writing linear or nonlinear, because that's not acceptable. You need to explain, especially since it says explain here, why you know for certain the difference, okay? Let's move on. All right, we can get through the example 5 pretty quickly. Identifying functions from graphs. Does the graph represent a linear or nonlinear function? Explain. Well, your first graph here. They're saying, does it form a straight line? No. This one is definitely not a straight line. So we would say nonlinear because it's not a straight line. Part B, this is a horizontal line at y equals -2, forms a straight line, so it's linear. Now you probably have noticed that part B here we've worked more with. That is all about your y equals mx plus b. So whenever your line is in that format y equals mx plus b, whether it's a graph or an equation or a table, you know for certain that it's going to have to form a straight line. Unlike part A here, which was really swirly right here, making it not a straight line. And you'll talk more about this kind of function when you get to Algebra 1, Algebra 2, but for right now, just knowing that they're not linear is definitely in the right direction. All right, your last example before you move on to your practice in your packet. Which equation represents a non-linear function? So they're saying which one does not follow the pattern y equals mx plus b. So we are going to look at each of these individually. So part A here, y equals 4.7. That would be a horizontal line at 4.7. That's linear, it's a straight line. So we can get rid of that. Part B, y equals pi x. Okay, that pi is kind of weird, but that just means that this is y equals 3.14x, approximately, because pi is just your approximation. But that just means that's your slope. That still fits this form. So that's linear. Part C, y equals 4 divided by x. Does that fit this form here? Y equals mx plus b? Not too sure, but we'll come back to it. Part D here, so we can distribute that 4, and that definitely fits this format. We've worked a lot with this. This is your beginning at -4, and you have a slope of 4/1. So this C, y equals 4 divided by x. So if you don't believe me that it's not a straight line, what you can do is graph it. Remember we did little tables in the beginning before we learned about slope and y equals mx plus b. I'm like, hey, if you're not quite sure, you can create a t-chart. So you don't want to plug in a 0. You can't divide by 0. But we can plug in a -4, let's say 1, and a +4. So we have 4 divided by -4 is -1. Four divided by 1 is 4. And here at 4 divided by 4 is 1. Okay. Now I'm just drawing a really quick sketch. Doesn't have to be anything beautiful. It's just to get you an idea of what's happening. So if we plot all those points, -4, -1, 1, 4, and then 4, 1. So we kind of have something going on like this. Definitely not a straight line. Not the best graph in the world either, just to kind of give you an idea of what's happening though. So some things that are nonlinear functions that pop up a lot would be things that have a nonlinear term. So y equals mx plus b is linear because the x in that formula there is always to the first power. So things that are nonlinear would be things like y equals x squared, y equals 1 over x, y equals x cubed, y equals the absolute value of x, things like that. So if you ever see any of these, you know right off the bat that they were in a different function family. They do not fit this linear function template. These are different templates along the way. So what you are going to work on now in your packet is the Now You Try. This is 1 to 5 in the next part of your packet. When you're done, you will show myself or the co-teacher, and then you will go on to your Go formative assessment. Remember, if you have any questions, you can rewatch, you can ask along the way, but make sure you're taking clear and accurate notes.